All right, today we're going to be working on yet another MacBook. This MacBook over here has a Bitcoin sticker on it. This MacBook has a Bitcoin sticker. I imagine he did not sell when it was worth $19,000 a Bitcoin, because this is an A1278, and they're getting it fixed in 2019. Let's take a look inside this MacBook and see what's going on with it. Here we have an A20-2936 MacBook. This is a 2011 MacBook Pro. That this A20-2936 is out of the machine. We are going to plug it into the charger and see what it does. Now this is taking 200 milliamps and not turning on. Typically an A20-2936 should be taking 5 to 700 milliamps when turning on. It's going to take 20 to 30 milliamps when PM Sleep S4L is missing. It's going to take 100 to 150 milliamps when every rail is turning on besides CPU vCore because ALSYS power good is missing. 200 milliamps typically means a short circuit to ground on PP Bus G3 Hot. Let's see if that's the case on this A20-2936. So I am going to open up a schematic and a board view. So we're going to go through our power rails in this machine and see what's going on. Power rails on the older pre-2013 machines are going to be on page 7 on this power aliases page. We get a light on the charger, and since we have a light on the charger, most likely PP3V42 is present, and I do not have to waste my time measuring it. So what I'm going to do is I'm going to check my PP bus. PP bus appears to be 0 volts on this MacBook. 0 volts here. Actually, never mind, I didn't have my multimeter on ground. My bad, bro. 12.6 volts, but not turning on. Okay, so next up, we're going to check some of the other rails here. Let's take a look at PPVRTC. Now you may wonder, Lewis, you just skipped over a whole bunch of rails. What's up with that? Well, PP3V42 is the rail that's required in order to power the SMC and the chips around the SMC that allow it to talk to the charger. So I have a green light in my charger. The green light in my charger means that the SMC chip, which is powered by PP3V42, is working. And if that is working to some extent, that means that this rail is working, which means I don't have to check it. Now, I didn't check PPDC-in. This is the DC-in power. If I have a light, that means that PP3V42 is present. If PP3V42 is present, then obviously the voltage coming from the DC-in board is present. So, for instance, let's say I'm having an issue where one device in my office, like my microscope camera, doesn't work. I'm not going to bother checking the voltage at my breaker box if one item doesn't work. Because if my breaker box were broken, then everything else that was on this circuit would also be off, like my monitor and my lighting. But since all that stuff is on, I know the breaker box is good. So I'm not going to go that far up the chain. This is simply a sub-rail of PP Bus G3 Hot, and I'm just not checking it because it's never missing unless somebody purposely removed a resistor connecting the two. There's a current sense resistor connecting these two that is almost impossible to corrode, and the only way that's missing is if some jackass removed it, which doesn't look like a case on this board. Next up, we're going to go for PPVRTC_G3 Hot. This rail is going to be there, and I'm going to tell you how I know this rail is going to be there later on. But first things first, we're going to see if it's present on this board. And also, I'm going to use this as an opportunity to just brag about my new toy lens. This is a $500 lens, and it does a lot of zooming, and it is sexy, isn't it? I know. I don't even have to use the microscope sometimes if I don't want to, because I have this lovely lens. Now, PPVRTC-G3 Hot is present. Now, how did I know that was present before I even measured it? Great question. When I decide that I'm going to plug the power supply in and figure out what the amperage of the board is, what amperage the board is drawing before I start, what I'm doing is I'm ruling out a set of problems. Now, PP Bus G3 Hot being shorted to ground, or a higher level rail being shorted to ground, is typically the cause of a 200 milliamp amperage draw from this machine. When I'm missing PPVRTC on G3 Hot, I'm also going to be missing PM Sleep S4L and everything else, and that typically means a 20 to 30 milliamp draw. My power supply here says that at 18 volts, I'm drawing 200 milliamps, which means that that's most likely not the case. This is why it's really important to make measurements for every one of these boards that you work on so that you can become more efficient over time. every time you solve a specific problem on the board, you're going to write down, here is what I did, here was the problem, here is the amount of amperage it was taking when I started. And eventually, if you're good at pattern recognition or have a half-decent memory, they'll also start automatically clicking to the point where you plug it in, and the moment you plug it in, you look at that, and you just take a look at the board and make one or two measurements, you know what's going on with it. And you can even get good enough at it if you really write down everything and you dig into what it is you're doing. You can get good enough at the pattern recognition to the point where you just look at the power supply and half of the time you know what's wrong with that particular model board. It's going to save you time, and in this business, saving time means making more money, retaining your sanity, and having happier customers. And having happier customers is a great thing. Now, we're going to take a look and see what other rails may be missing. So let's scroll up a little bit over here, and let's check PP5ES5. I'll do that in the microscope this time. I will stop being lazy. And PP5ES5 can be found right over here. 5 volts. Okay, next rail, we're going to check for PP5ES3. PP5ES3 is going to show up on these capacitors over here. Let's see what we have on the capacitor. Okay, when we try to measure the capacitor, it looks like we have 0 volts on that line. Now, I have a PowerPoint presentation that I made it in LibreOffice, so I guess LibreOffice presentation, but PowerPoint sounds cooler. Microsoft is really good at branding. That's why I think they do well with stuff. Linux has a terminal. Microsoft has PowerShell. It's for the the Alex Joneses of the world. PowerShell. PowerPoint. Anyway, I had a PowerPoint presentation that gives you an idea of how it is you troubleshoot certain issues on certain rails. Certain issues in the machine. Repairing using data and logic. Love it. Do it myself every day in the automotive world. Awesome, Jay. I hope you enjoy the detective work. That's what makes the job fun. So what I have here is a document that's going to show you how it is you find the power rails that are missing and all this kind of good stuff, and how you troubleshoot and learn how to do this the way I do. And it's a beginner's guide that is in my links down below. And I will show you it on screen here for just a moment. Just a moment. Just one moment. Bam. And on the Power Rails page, I tell you how it is that you should go about figuring out why a power rail is missing. So if a power rail is missing, a couple of things are possible. The first is that it's not being told to turn on. So here I have my microphone. This is for my transmitter. Moment, because you are not able to hear me for that moment because I told my microphone to not turn on. It wasn't an issue of power. It wasn't an issue of a broken mic transmitter. It was an issue of I was not telling it to turn on. You also have no power issues. So even if it is being told to turn on, could be a short circuit to ground. So let's see which of these is going to be true for this model board. So the first thing we're going to do is figure out where PP5ES3 is created. So let's see how it is we would go about finding out where PP5ES3 is created. So I'm going to right click on that, I'm going to bring up my board view, and I'm going to keep clicking on PP5ES3 until I find a page that looks like the page that's responsible for making it. Many of my students in the past had lots of problems telling the difference between where power was going into something and when it was coming out of something. So for instance, here is my microscope camera. I have power going into it here. So this is where the voltage is going into my camera. But this is not where the voltage is created. The voltage for my camera is created at that wall wart power adapter, something that looks like this, that is under my desk. So this is where the power is being created, and then this is going to be plugged into something where it's going into that. So let's just plug this back in, and I'm going to show you the difference between those two things, since it happens to really confuse a lot of people that I've had here for training. So if we click PP5ES3, I'm going to show you some examples, and we're going to go over how it is you can tell those things apart. This is PP5ES3, but this is PP5ES3 going into a transistor. PP5ES3 is pulling up a signal with this 100 kilo ohm resistor. PP5ES3 is pulling up memory set ISIL LS5VL. PP5ES3 in this scenario is not being created here. That's not what we're looking for. So we're just going to click again. Here, PP5ES3 is going into the webcam connector to power the camera and the automated light sensor. That's what ALS stands for here. Over here we have PP5ES3 going into the hard drive connector. So that is not it. That's where it's going to be powering the hard drive. Here, that's the optical disk drive power. Here we have PP5ES3 going into a USB power chip. So this is what's going to power the USB items that you plug into the machine. See, PP5ES3 is going into that. So that's not where we're looking. We're just going to keep scrolling through this until we find out where it's being created. Same thing is true here. This is it going into the chip that powers that little infrared remote that Apple used to use in the front of the machines. Not it. This is it going into a sleep circuit. We want to figure out what chip PP5ES3 comes out of. What creates it? This is it going into an audio supply, into an audio chip, into an audio chip, into another audio chip of some sort, I imagine. And we just continue. And this is it going into a FET that's then going to be creating another rail, PP5ESO. So let's continue scrolling. So here, PP5ES3 is coming out of a chip called TPS51125. So let's find TPS51125 now, shall we? All right. TPS51125 is going to be U78200. You're right. So here, PP5ES3. Look, I found it. PP5ES3. Now, this is coming out of here. So this is a buck converter. This chip is telling those two transistors when to switch, and they're going to turn the 12 volts that are coming into them via PP-bus S5 into 5 volts out of it. And it's over here, 5 volt, 3.3 volt power supply. So, let's take a look at at how this is created and what's going to tell it to turn on. Now, if you take a look, N-trip 1 is most likely going to be what turns on this chip. So if we were to select TPS51125, what I'm looking for is an enable pin. Here we go, N-trip. Connect a resistor from this pin to ground to set threshold for short to ground to shut down a switcher channel. Okay, so a lot of chips, what they do is they have what's called an enable pin. So you send voltage to the enable pin and then it turns itself on. Similar to how turning a light switch turns the light switch on, sending 3 volts to the enable pin will turn it on. N-trip pins are typically the opposite of enable pins. A device with an enable pin is going to be off unless you tell it to turn on. A device with an N-trip pin is going to be on unless you tell it to turn off. That's the difference. So with this device, the way it works is you have to turn it off. It's going to automatically be on all the time. So let's see how it is they managed to do that in the schematic. So if we take a look, N-trip for our rail that's missing. So this over here gets tied to ground through this transistor. So this chip is always going to have its enable there. It's always going to be wanting to turn on. But this transistor over here is going to short that to ground to shut down the switcher channel when this signal is present. So this here is an N-channel MOSFET. The way an N-channel MOSFET works, and you can figure this out from reading my document if you are at all intimidated by this. We go over how this works, and this document is 110% free. It's not like I got a paid version of it that features all the shit that you gotta, for the real version. All of this stuff is really like kindergarten level stupid, and it's designed so that even somebody like me may be able to learn something from it. Now, back to the PDF. Over here, this is an N-channel MOSFET, which means that when the voltage on the gate, G, is higher than the source, S, then this will allow the voltage to flow from drain to source or source to drain. And over here, our source is ground, which means that any voltage on the gate, anything at all, is going to allow this to open, and it's then going to send our switcher channel to ground, and it won't work. So if P5VS3 enable L is present, it will turn this transistor on, which will stop this from working. That's why it says underscore L, by the way. P5VS3, the name of the power rail, underscore EN, enable it, underscore L when the signal is low. So this signal over here, enable this power line, enable P5VS3 is going to be asserted when the signal is low. Because when this is high, this transistor is going to open and or close is the correct term. You get it. Send power through, and then it's going to go to ground, and then the N-trip will be shut down. So the first thing I'm interested in doing here is checking out the N-trip pin. Are you actually being told to turn on? I'm also interested in checking out P5VS3 ENL. So let's see where that is going to be on the board. We're going to take a look and see where that is on our board. So if we take a look at Q7221 over here, at Q7221, you are going to have the P5VS3 ENL. Now, I think that that rail is actually present and shorted to ground. I think that based on our amperage usage. And before I even measure this, I'm going to tell you that that enable signal is likely going to be present. The reason I'm saying that is because it's taking 200 milliamps rather than 20. It takes 20 to 40 milliamps when the signals are not present and it's not trying to make those rails. It takes 200 to 400 milliamps when the signals are present and it is making those rails or is trying to make those rails, but it's being shorted to ground. Again, one of the ways that you get much faster at this and much more efficient, especially if you're working on the same device over and over again, or the same small set of devices, is every time you figure out what your problem is, whether it's through your 1 or your 2 or your 3 hour troubleshooting process, you write down all the symptoms the device showed, you document it, you don't plug it into a regular MagSafe, you plug it into something where you can measure the amperage, and you remember your measurements on different power lines or different rails, and then you can then associate those with specific problems. So I'm going to make the guess that this signal over here is actually already present on this board. We're just going to double check and see. And Lewis, your trousers are unzipped. You may show more than you expect on crotch cam. Maybe that's by design. Measure. And as you can see, we have 3.5 volts, which means that this is being wait a second. No, that's not being enabled, because that's only enabled when it's low. Okay. Lewis may have been wrong here. So P5VS3 ENL. P5, that means if this is high, this is purposely going to be sending P5VS3 enable L to ground, and that's no good. So let's try and figure out what's going on here, and let's also see if that's steady or if that's pulsing. I may be right after all. Okay, interesting. It's going back and forth, and it's pulsing. Now, one of the reasons it could be pulsing is because there is a short circuit to ground. It could be detecting that there's a short circuit to ground and then turning the chip off to protect itself. Let's see if that's what's going on. We're going to measure to see if we have a short to ground on the output where PP5ES3 is. So I'm going to go over here to where these capacitors were, and we're going to see what the resistance to ground is. 11 ohms. Well, you can't see that here. Now you can. 25 ohms, 31 ohms, 39 ohms, 50. Interesting. We had something similar to a short, but it appears to be going away. The short circuit appears to be curing itself. Imagine that. Much interesting. Wow. The self-fixing board. Yeah, we're up to 6 kiloohms at this point. Okay, now I'm going to do something that's a little experimental here, since I don't see much in terms of obvious damage. I am going to remove that transistor that is going to keep this chip from turning on and see if my rail is created. So if you look at the schematic in board view, you'll see that, like I said, that the N-trip signal has to be high. If it is sent to ground, it will shut down the switcher channel. And Q7221 is what's responsible for shutting down the sensor channel. The switcher channel. So I'm going to remove that chip and see if that has any effect on our rail being made. What I'm looking to do here is see if there's an issue with the chip or with the the stuff that's making the enable circuitry. Is the stuff that's making the enable circuitry turning off because it sees that there's a bad chip, or is there something else to it entirely? There's only one way to find out. We're going to take this chip off and move it to the side, where the chip will be sitting sideways. So we've disabled its ability to tell itself to shut down, for the system to regulate it shutting down. And it is capable of making 5 volts at that point. So the circuitry itself is good. This chip is good, the transistors are good, all of that is good. What we need to do is figure out why the system is telling it to do that. That's where the fun comes in. So this is very strange, because at this point we have no reason for 200 milliamp amp draw. There's nothing on this board that could really use 200 milliamps at the point in time, because we're not entering an S3 state. Yeah, there's nothing in an S3 state here, so it doesn't quite make sense. What the F is going on here? Well, I do still have this thermal camera here that I have not unplugged yet, and since it is right next to me, I might as well make some use of it. So if you direct your attention to the screen, you will see a thermal Pepe. Thermal Pepe is the god of short circuits, king of the Andals and the first frogs. Protector of the realm. Okay. Now, as you can see, there's about 50 Celsius is being used right over here. And if we turn the board around, you'll see that what is getting boiling hot is the platform controller hub chip. Now, the platform controller hub chip is powered by PP3V3S5 in the beginning stages of the machine turning on. And the PP3V3S5 is a rail that's created by the chip we saw, and it's told to be created by this chip over here, which is the SMC. So the SMC tells this chip, create PP3V3S5. The PCH tells this chip, create PP5ES3. So this chip is doing fine. It's not that the PCH, it's not that that chip creating the 5 and the 3 volt rails is bad. It's that one chip that's supposed to be telling it to do what it's doing is doing its job, and the other chip that's supposed to be telling it to do what it's doing is apparently, seemingly burning, just sitting here and burning. So we had one machine tonight that had a bad PCH, that did not have a bad PCH originally. It looked like one cap, but then was bad PCH. At this point, we have yet another machine that is a bad PCH, which we're going to leave in the status for Paul. If you need something to be worked on with BGA rework, if you need the Zalmo, if you want to outsource a job that requires browsing eBay and AliExpress and Golden Chipset and all these other CIC vendors to spend $50 to $80 a piece on chipsets that may or may not work, that take 45 minutes to solder onto the board, that you cannot return if the chip that you bought was soldered before, even if the chip itself is bad. If you want those types of jobs that are only done on a commission basis to be performed live, on camera, with a Zalmo that is on Paul's S's desk, don't delay. Send your machine to 186 First Avenue, New York, 10009, Rossman Repair Group. Attention, Paul. If you have a pedantic repair job that will likely waste hours of time and not only not make money, but cost money to do, send your machine to Rossman Repair Group. Attention, Paul. Paul is soon going to have a Zalmo on his desk that he's going to be using to work on all of these lovely boards that are just so easy to fix. It just needs a little bit of your soul. So this board has a dead PCH, which means that on a machine that is this old, given the amount of work that would have to go into replacing the PCH, thank you very much, Insane Wall, I really appreciate that, it's very kind of you. On a machine that is this old, that is a complete and utter waste of time. Because even if you do win and spend 45 minutes replacing a single chip after doing all this diagnostic work, even if that chip does work, which, let's face it, fuck it, it is eBay, it is CIC, it is Golden Chipset, it is China, it's not. Even if that BGA chip you get does work, that's quite a bit of time you spend to fix a sandy bridge. And at this point, with the amount of time I've wasted tonight, And the amount of no fixes I've had, I'm feeling quite sandy as well. So let's go over before I end the stream and ride my bike off the Williamsburg Bridge. We're going to go over why it is that PP3v3S5 was being created, but PP5ES4 was not. So we're going to take a look at that signal that we were required to get PP5ES3 working. P5ES3 enable L needs to be low, remember? So let's see where P5ES3 enable L comes from. P5ES3 enable L. This is going to be a signal over here that can be pulled to ground and made to go away. Remember, this signal has to go away. It has to be low in order for the P5ES3 to be enabled. So Q7911 is an N-channel MOSFET that will open when the voltage on the gate is higher than the source, and here the source is ground. So it will allow this signal that we need to get rid of to go to ground if there's voltage in the gate. And the voltage in the gate is going to come from PM sleep S4L. PM sleep S4L comes from the platform controller hub over here. And the platform controller hub is the chip that I just showed you on my Pepper thermal cam as being on fire. So we have PM sleep S4L going out of U1800. U1800 is platform controller hub. And if we take a look over here, you'll notice that platform controller hub, when we plug the board in, we're going to take the MagSafe, do this. 57 Celsius, and it's not even on. This is junk. Complete and utter junk. I'm going to go cry now. I'll see you in the next stream, and as always, I hope you learned something.